that you then will use in that box. We can talk about various versions of algorithms, but it doesn't matter so much the process, but it matters that we do this on the basis of some data that came from somewhere. And that data can encode biases. So for example, if you look at the distribution by gender of occupations in the United States, you can see there's very, very strong gender bias in some occupations for whatever reason. Those are the facts on the ground. This is the historical data that we have access to if we're going to train an algorithm. Now, one thing you might do if you're going to train an algorithm, for example, to suggest job ads to potential candidates, is you could try to make a prediction about where they'll succeed. And if you use historical data, you might naively, accidentally, then say, well, women are much more likely to succeed as kindergarten teachers, or pre-K teachers, or as nurses than men are, and you might accidentally, very naively replicate this. But it can also happen in more subtle ways. So let's use the example in our heads of we're interested in making loan decisions, or credit scoring. We have access to historical banking or credit histories of real people as our training data. And if those past loan decisions, for example, for whatever historical reasons, were biased against women, women may have had fewer loans in the data set. They may have had fewer chances to prove their ability to repay a loan. They might look riskier, maybe. And that signal could be picked up on in making predictions.
I would expect, in fact, because there are fewer, which means that the bar is higher, the probability of them returning the loan is higher than for men.
That's another possibility. That would be another form of bias that you could get. If women, for example, for whatever reason, historically were given higher interest rates than equally qualified men, women might have repaid at lower rates. You can tell opposite stories in all of these things. I'm just giving examples. And that would be encoded in historical data, and maybe would be reflected in future predictions. Or maybe, for whatever reason, historically, we were just worse at understanding which women would repay. We were very accurate on men, and we kind of gave the loans out to women sort of at random. We didn't know who to give them to. That could have resulted in a situation where women might look like a riskier bet because we would have given the loans to the wrong women, and they would have repaid perhaps at lower rates. Questions?
It seems like all of these examples still require that the algorithm somehow receives this input, whether the subject is male or female. It seems like the easiest thing you could do is say, okay, I'm going to design an algorithm that doesn't receive the gender, race, whatever of the person, and doesn't seem like it could, like any of these things matter.
That's a great point. Let me repeat it because it's a really important point. The question is, can't we just get rid of this problem and be done with these 2 lectures right now by saying, let's take our data, let's delete the sensitive attribute, and then let's go forward happily ever after. We have no possibility of being unfair. What can go wrong with this idea?
We get to random decisions throughout everything, get a random decision.
So
No, but also other attributes might be correlated with gender. So
Your bank will make less money.
there's a bunch of concerns. There's a concern that some of these attributes may be actually
Occupation.
causally related to the thing we're trying to predict, and so we could become much, much less accurate and make much less money if we throw away these attributes. But there's another concern, which is that if you have rich enough data, then those sensitive attributes are well encoded in the other non-sensitive attributes. And any machine learning algorithm worth its salt will easily automatically recover them and propagate whatever bias it wanted to based on what it was optimizing for. That's a point I was going to try to return to in a little bit, but it's a really important one because that is, in some sense, the most common approach to this fairness problem in the world today, which is to attempt fairness by blindness. To attempt to say, okay, if we just don't see the explicit sensitive attributes, maybe we can tell ourselves that we're okay. What happens in practice is then it becomes harder to see that you're actually still unfair. Yes.
Another issue might be that you actually want to do affirmative action, and that
Yes.
would prevent you from doing that.
And even if you don't, so Michal's point was you might want to do affirmative action. If you don't have access, you can't do that. But even before you get to affirmative action, as we're going to see as we go along, in order to ensure other notions of fairness, which you might not even interpret as affirmative action, because I don't know how to mathematically, I don't know which formalization of affirmative action you want to take there.
In a broad sense.
But yes, there can be notions of fairness that you can't achieve without access to those sensitive attributes. So this is going to be a fundamentally challenging problem that, and on the one hand, you want to say, I don't want to look at these. On the other hand, you really, really, really have to look at these in order to do a reasonable thing to sort of, in general.
So some of the problems on this slide can be interpreted as simply not having enough data.
Absolutely.
For example, if women had higher interest rates and so we paid less, that could be corrected for by looking at the rates that they actually face and making a proper adjustment.
Absolutely. One of the issues that's very common is that we just don't feed our models rich enough data, and then potentially we can do better. Particularly if in your mind what you're carrying is a notion of fairness as accuracy, then just having richer and better data to the point where we can make perfect predictions gets us a lot of progress. So that's something we'll definitely return to. It's a great point. Issue number 2, not having access to the data that it needs. You might have problems with some populations being sparsely represented in your data or underrepresented in your training data for a variety of reasons. It can be hard to be right on those categories if you just don't know enough about them. Or as we were just discussing now, some populations' outcomes might be better predicted by data that you didn't make available, either when you were training or when you were deploying your classifier. You may not even know this because you may not have gathered this data in the first place. But it's in many situations where we're making consequential decisions, this is actually a realistic issue. It does come up. Another consideration is that this issue of privacy sort of revisited. Somebody may have at some point told the organization, you got to delete the sensitive attributes because we're worried about privacy, or because we're worried about fairness, we think it's going to solve the fairness problem, and then you end up in a situation where you're much worse off. The third set of reasons, in my mind, that we see unfairness manifesting in the real world is that we weren't optimizing for some mathematical notion of fairness in the first place. We were optimizing for other stuff. One category of issues is that for a lot of reasons, we value model simplicity. Maybe it's because we want explainability, maybe it's because we're trying not to overfit. But model simplicity may prioritize accuracy on the majority population at the expense of accuracy on the minority populations. Because if among my set of simple models, there's one that does well on 87% of the population, there's another that does much, much better on some minority population and slightly worse on the majority population, we're going to pick the one that goes for the majority, depending on how we've set our optimization. Yes?
I would argue that even given the same accuracy, there's a lot of local minima, and the model would prefer those that are simpler to learn, which are to, like, M versus N.
Yeah. So there's this is actually, I think, a major issue for us. And then, as we'll see, as we go along today, some fairness notions are inherently in conflict with each other, or inherently in conflict with accuracy. And if what you did was you said, I'm going to design the most accurate model that I can, because that seems like a pretty reasonable thing to do, you may have unwittingly made a major sacrifice in some notions of fairness. I'm not saying that's wrong, I'm not saying that's right, but I'm saying that's a reason why we see unfairness manifest in the real world. So returning to this question of can't you just delete the sensitive bits, I think we already covered this well. If you've got rich enough data, it's going to have good proxies for your sensitive attributes. Proxies can be complex functions of the data that you have available to you. They don't have to jump out at you as obvious proxies. And machine learning algorithms, this is what they specialize in. They're good at accidental inference of this, exactly this sort. And even if, these proxies aren't very good and this inference isn't very good, you can still have big consequences of these proxies being available. Even if it's, 70% of women have career breaks versus 30% of men, that's present in the data, but you've eliminated gender from your data set, an algorithm that biased against career breaks is still going to have an outsized effect on women versus men. Again, as we said before, some differences that correlate with group membership might be justifiable basis for different treatment. Others might not. What are we supposed to do? So, the plan is to try to make a little bit of sense of this kind of uncomfortable situation. What I want to do with you in the rest of the session and the session that we have this afternoon is talk a little bit about specific notions of classification fairness that have been studied in this algorithmic fairness literature. It's not going to be clean and neat. It's going to be a mess in kind of an interesting way. This afternoon, the plan is to really show you this mess in the sense that you can't always get what you want. We're going to see some uncomfortable conflicts between these various notions of fairness. And then, time permitting, I can give you a little bit of a sort of quick overview of what's going on in this algorithmic fairness space. Okay. So our mission now, though, is to get ourselves some notions of fairness. We need some math here. At a high level, the literature in this space has treated individual fairness notions and group fairness notions, sort of two categories of approaches. I'm going to spend much more time on the group fairness notions, but first I want to talk briefly about individual fairness notions. So individual fairness notions specify some sort of constraint that should bind at the individual level. And the general flavor of these kinds of constraints say something like, any two people who are similar according to the task at hand should receive similar treatment. So you could try to write this as an equation that says, if we have some notion of closeness of the outcomes, so an algorithm's going to get a person X and a person Y, and it's going to produce some sort of treatment or outcome or label or prediction, whatever it is. We want those to be close according to some metric in situations where those people were close in some metric. So the idea here is that if we know what it means to be similar according to the task at hand, we know what are the sort of legitimate dimensions that should matter, for example, for credit scoring. And we know what are the illegitimate dimensions that shouldn't matter for credit scoring. Maybe we decide that gender is illegitimate, but number of years of employment is legitimate, whatever it is. Then we should be able to say that people who have, for example, similar numbers of years of employment and are similar in all the other legitimate dimensions should get, for example, similar credit scores. That would be the kind of thing we could enforce here. The good thing about this flavor of definitions is they manifest at the individual level. This is a guarantee to you and to you and to you and to you and to you that you're treated similarly to the people who are similar to you. We're not going to get that as we go on to the other fairness definitions, so enjoy it for the moment that we have it. The con is I didn't tell you what this is or this is, and I don't know who can tell you what they should be. Essentially what individual fairness notions do is they shunt all the hard work of understanding what fairness is into defining these metrics, and nobody knows how to pick those metrics. Now, there has been literature that explores this space and says interesting things. I mean, this is an interesting mathematical demand. You can play with designing algorithms that achieve this given access to metrics, and we have a literature that does that, and it's nice. But who picks the metrics? I don't know. So that's why I'm going to leave individual fairness metrics for now, but if anybody wants to ask about them or comment about them, now's a great chance.
In a sense, if you have these metrics, you have your algorithm, don't you?
Exactly. This basically just sort of sweeps everything under the rug. It is a very neat and pretty way. Exactly. Yeah. Other comments about individual fairness?
Well, you're basically bumping into the problem that mathematics looks looks to optimize a single function. And this complicated process that you're summarizing as a single function has, oh my God, I forgot, 1,000 other characteristics that are not extractable.
Not-
And are not extractable if you see only the result.
So yeah, so I think that's exactly, sort of some of the discomfort here. Somebody's going to pick a metric, and then somebody else is going to come along and say, no, of course you needed your metric to take into account this other consideration. Maybe it was present in the data, maybe it wasn't present in the data, but I see no end to this.
Transparent discussion.
It raises a great discussion. It raises a great discussion that some experts should have somewhere, but I don't know how you come to a consensus on this, and it doesn't really solve anything. It's the same discussion we needed to have before we had this notion at some level. It's an important. I think it puts a point on where the discussion might need to happen about what are the legitimate bases of decision making for this particular type of decision. It's important to put a point on that. It doesn't solve the problem for us at some
But
level.
this is precisely the problem we're trying to solve.
This is the yeah. Chicken and egg kind of thing going on.
Isn't this the exact problem that the Biden executive order is trying to address on AI safety and secure, especially around loans? Like it's the individual level?
I don't know well enough to say with regard to the executive order.
I'll just propose as an example to think about. A company wants to hire the best person. And they end up with a definition, and they'll hire just one type of person forever, and that's not, and then somebody later says, oh, we need a variety of people to do our job in the best way. And we don't have algorithms for coming up with the best group of people.
Yeah, so cohort selection is a really interesting question. Let's maybe set it aside, but it's a good thing to keep in the back of your mind. That's a rich and interesting one. Okay, so if you'll allow me, I'll say individual fairness notions. There are things to say there, but I think maybe we get to a sort of a richer discussion in some sense by moving to talk about group fairness notions. So here what the move is going to be is we're going to pick fairness notions that essentially say some particular statistical relationship should hold similarly across, that should be an of, different groups of sensitive attributes. So we're going to somehow say, here are the different ways we want to cluster people by their sensitive attributes, maybe men, women, maybe it's going to be about race, maybe it's going to be about age, maybe it's going to be about something else. And then we're going to say that there should be some statistical property that should be behaving similarly across these various groups. So notation for the rest of this discussion, we're going to live in a very simple world in which individuals consist of a bunch of features X that are going to be available for training and for classification purposes. Individuals have some true label Y, and they have some sensitive attribute, which is going to be they're belonging to a particular group. Maybe they belong to more than one sensitive group. And then we're going to be designing scoring rules which have access to those features and those sensitive attributes and produce labels or predictions for people. We'll look at various variants and restrictions on this space, but this is sort of a high level, the flavor of setting we're going to be in.
Sensitive attributes and features are disjoint.
So features can certainly encode the sensitive attributes, or not, but we're making it explicit that the algorithm has access to the sensitive attributes. So it's possible that there's a strong correlation between the X's and the A's. In fact, probably realistic. But I just want to give you explicit access to the sensitive attributes.
No, but at the individual level, what the coordinates in X and coordinates in A are disjoint. There is no coordinate that appears in both. That's what I'm trying. Statistically, there could be correlation. You look at the joint distribution of X and A. I'm not talking about that. But those are different coordinates.
You could imagine a
the
situation.
same coordinate appear
You
in
could
both.
imagine replicating A as one of the coordinates of X. That's a possibility. Well, let's return to that as we get a little bit more concrete.
You're
Yes.
saying,
There are three. We can go in any order.
Be fair, be fair. Let's see how you do it.
but you're saying that the true label, Y,
to depend on A, you're going to need to encode A in your X. But I'm not a priori saying that it is or isn't encoded there. It may be fully encoded there. It may not be present there.
That's why I wanted to be clear where the
Yeah,
line,
yeah, yeah.
where the line goes. That
Yeah,
there is
yeah.
a clear line.
So you're saying, sorry.
We'll do 1, 2, 3, 4. Yes.
No, any relationship between F and R? I mean, R is for the purposes of F, no?
Absolutely, but I haven't said anything about it yet. So far, just R is going to be some prediction. We hope it's good. We hope it's meaningful in some way. We haven't gone to talk about that yet.
About the context where F would depend on R?
We're thinking about a context where no. F is some true underlying. This is the true underlying label. This is how you, given your sort of true features, how we uncover your true underlying label. R is some attempt to predict these Y's.
So Y is like
So
your true
Y
probability of
is the-
becoming the loan, whereas R is your prediction given whatever you know.
Perfect.
So what I use the true ranking that you would like to have?
Yeah, so the Y is some fundamental truth about whether you'll repay the loan or whether you'll succeed in the university or whether you'll be a good job candidate. One could then ask whether or not that's the only thing we care about in prediction. I haven't gotten there. I haven't yet given us an objective. But so far that's truth. This is some prediction, which we're going to somehow say something about how maybe we want it to interact with the truth. And these predictions are allowed to depend on these sensitive attributes, which can be encoded in the X.
So you want to minimize the distance between Y and R, right?
That seems like
That's
a
all.
legitimate thing one might want to do. Yes. Was there something that looked like a question here? You got that? Okay. 1, 2, 3. Yes.
Yeah, so within the sensitive attribute, all the labels are the same for us.
Not necessarily. No. So it's not that all women have necessarily the same true label by any means.
I
There could be
mean, okay, if we're talking male, female, then male are sensitive and female are sensitive, or only female are sensitive, or only male are sensitive.
So just think of it as there's a series of bits that
Yeah.
can be associated with any individual that we're going to call sensitive attributes.
Okay.
In your mind, if you want to assign them to binary membership in categories of various sorts, you can do that. If you like to think of things like gender being binary, and so you could think of it as membership in the female group versus not membership in the female group, membership in the Caucasian group versus not membership in the Caucasian group. These could be the kinds of things you can encode with these binary attributes. We'll get back here. Michal, you wanted? There was something floating here. Yes.
If F is a deterministic function, then you're assuming that X contains everything that determines the outcome.
F need not be deterministic, but it's a great thing to keep in mind. Yeah, so if F were deterministic, then X would encode everything we needed in order to get to the true label. Instead, we could have, this be some randomized mapping. Yes.
So it's again the same, more or less the same thing. If I take X and A, and same X and A prime, Y is going to be the same. That's
Say
an
that again?
assumption.
If we take,
That the outcome for pair XA and for a pair XA prime, where X is the same and A prime may be different, what you call outcome Y is the same. That's what you're assuming, right?
that's the assumption to the
Yeah, now
extent
that-
that you want a dependence on the A's, you have to have them encoded in the X's. Yes.
Okay, now, that could be that Y is the outcome, like deterministic, or maybe this, or maybe it's the average over all A's of the outcome. So those are different interpretations of what that Y means. Okay, so I'm wondering which one we should keep in mind.
Good.
It's the average over the population over all A's, or it is something which is constant over A.
So
Those are
A
different.
does not have predictive power.
I
But
don't
A-
care about predicting. She's talking about the outcome, the truth. the
Right.
truth.
That's the
Right.
So
predictive
there is some
power.
truth
So-
there. I want to know if the truth is constant over A, or that thing Y is the average over A for fixed X.
It's
Those
not
are two
it's
different
not necessarily
models.
constant over A. Not necessarily
Or
constant over
statistic,
A.
Y could be a random variable, which means the distribution
Why?
of Y.
Yes, exactly. So we have a.
So it's the statistics over when I take A, but then I have to know what the distribution of A is. And that's, maybe it's correlated with X. So then I don't know what it exactly means. I mean, There is here some vagueness that I don't know.
Yes, so
what the problem is.
okay, every value of x induces a distribution over y's. And if you would,
That implies a distribution over A. Which
if
is,
there's a correlation
which may be
between x and a,
dependent-
then yes.
Which may dependent on the value of x.
Yes.
Okay.
These are exactly the sorts of issues we're going to get stuck on in just a moment.
You thought that would be an easy slide, right?
It's not.
Okay, so let's get into exactly these sorts of issues, which are the correlations between these various concepts and what we expect of them. So I'm going to talk
There's a
today.
question there.
Oh, sorry. Yes.
Maybe you're already coming to this, but is it also just practically worthwhile pointing out, the good example is if you look at a photo of the US Supreme Court bench in the 1960s, a machine would learn you need to be white, Anglo-Saxon, male, and Protestant. And the distributions can change. I mean, that's one of the, to your point about the best candidate, those algorithms are so bad because 40 years ago, the best candidate probably was male because women weren't graduating at the same rates. And
Absolutely. Yeah. So I think it's an important thing to carry in all of this in the backs of our minds. The data is changing. The goals are changing.
the distributions are changing.
Everything is changing. I'm not going to solve that problem, but it's present. Yes.
Solve it for one period.
Yeah, exactly. Okay, so I'm going to talk to you about three different group fairness notions. In some sense, I'm going to give you three different things that we might interpret as a fairness criterion. I'm not going to claim that any of these is the right fairness criterion, but I'm going to claim that if you were auditing an algorithm that was being used for credit scoring, and you saw violations of any of these, that maybe you should think of it as a red flag. Maybe you would want to understand why there is a violation of this criterion. Maybe you would then go and decide that it's acceptable, it's reasonable, but that these are the kinds of things you might use as red flags. These are three examples of these kinds of group fairness notions, which are enforcing some sort of statistical property across these various, across membership in these various groups. One can generate, by the same sort of methodology, lots and lots of other group fairness notions. So you should keep in mind that these are not the three notions, but rather three particular notions that have some, I think, appealing looking properties, some unappealing looking properties, and some interesting interactions. So let's start with independence flavored notions of fairness. What do we want to say here? The idea is that one fairness criterion might be that the labels that we give are independent of membership in protected groups. So one name given to these kinds of independence notions is statistical parity, which demands that the classification that an individual receives is independent or nearly independent of their protected attribute. So for example, the probability that you're going to get a high score according to our algorithm, given that you're female, should be similar to the probability that you get a high score given that you're male. And that should hold more generally for all pairs of groups A and B that you might look at, for all possible scores or outcomes or predictions that might come out of our algorithm. The probability that we generate that particular prediction, given that you're a member of A, should be similar to the probability we generate that prediction given that you're a member of B. Before you complain about this as a notion of fairness, which I know you want to do, what's good about this as a notion of fairness? Is there anything you like about
It
this?
assumes equal distribution of merit.
Great, okay, so I don't know if that was a complaint or a...
No, that's a good property, because if you want to argue that the distribution of merit between males and females of brain power, that's a argument for the neuroscience department, and we'll get a lot of trouble with women in the room.
So you're saying-
distribution of merit is equal, or some property is independent of your gender.
So if you think that, yeah, so let me just reflect this back, and then I want to hear more positive-ish things about this as a notion of fairness. So you're saying in some sense, okay, if we really take it that these protected attributes should not be relevant to the task at hand, or we have no reason to believe that they're relevant to the task at hand, this is a clean way to say we should really not see them playing a role here. We should just see nice, clean independence. Yeah, there was another...
I think just to rephrase it in my head, it is more like if was independent, like, let's make sure that like the algorithm is, has, like the prediction is independent.
Yeah, in some sense, this is why I said think of these not as the notion of fairness, but maybe as a red flag. If when you were auditing that algorithm for assigning credit scores and you saw that it didn't have independence, that there was a strong correlation between membership in a particular group and the score that people were given, you might not say throw the algorithm away, but you might say why? What's going on here? Yes and then yes.
So I think it's two sides of the same thing. It needs you to pre-identify the groups you care about. So there might be a protective group, even an intersection, you do this for male, female, you do this for Jewish, Arab. It doesn't imply Jewish female, for example, or something like that. That's one. Second, in order to audit, you need to observe who's in which group, which for disability, for example, might be a problem.
Great. Those are all excellent points that I hope to talk about a little bit toward the end, but they're all points that really I'm not going to address head on for most of today, but they're super, super important. Both the sort of the visibility issues, the sort of intersectionality issues, or sort of the interactions between membership, and the need to identify the groups in advance. I'm going to hold all of those, and time permitting, maybe we can return to a discussion of how the literature starts to grapple with some of that.
So coming back to my question on previous slide, this makes perfect sense if y is a function of x, which means it's constant over a.
If y is a function of x,
So xa and xb give you the same y. It's a constant. If y is a distribution, when you take the distribution of all possible a's, this makes no sense whatsoever.
well, it makes sense mathematically, but you
I mean,
just may not like it as a
but
fairness
it's
notion.
not-
There's
it's
two
not-
kinds of
it's not
sense
something
here.
that I want. Because
Yes.
maybe that hidden thing is exactly the one that determines, all those with small a are high, all those with small a equals small b are low. And that's it, I'm done. I mean, I've thrown out the baby with the water.
Absolutely, yes.
I need to comment on that. I think it's the wrong way to look at this. I think if A has like any predictive power, then A is already encoded in X. So it's not like A is independent of X. A can be a subset of X for all we know.
That's it. If indeed y is constant over a, which means that everything that
But
is
it's not
relevant to y
restriction.
is already in x, that is okay.
Yes,
But
yes.
she didn't say that. She did not want to commit to that interpretation. So,
So I think what
want
you're
to keep it
saying is
fair.
that there.
I want to keep it fair.
Yes, I'll try to be fair to you. But I think what you're saying is that in some situations, this is a restriction that would force us to give totally useless predictions. Fine, I'm okay with that. It's just a restriction. So you guys said it's simple. It's relatively easy to ensure an audit if we have access, as you guys said, if we have access to those protected bits. And it's sort of reflected in some laws and sort of regulations. It can be useful as a red flag. If you see that there's a correlation that you weren't expecting with a protected attribute in terms of the behavior of your algorithm, you should ask yourself why. What do you not like about this? I think I've already heard grumblings in this direction, but what do we not like about this as a fairness notion?
Sometimes the gender is relevant.
Sometimes the protected attribute is really, really relevant to the prediction task, and maybe it's legitimate to use it. And in particular, I think some of you even said, we might see different distributions of qualification based on the protected attribute. And in particular, in those cases, we get a conflict with accuracy. And one of the other things that maybe you didn't say is this doesn't force you to give the right women the loan. It says we have to give, if we're giving 20% of men the loan, we have to give 20% of women the loan. It doesn't say that we have to give it to the qualified women. So that already sounds like it could potentially enable some unfairness within the group of women. So, okay, not perfect, but potentially a useful red flag. Let's move to another notion, which we'll call separation class of ways of thinking about fairness. These we want to say conditioning on y. What was y? The true label, yeah. So conditioning on the true label, I'd like independence between what and what?
The prediction.
The prediction and the protected
So
attribute.
if two people are both equally good at, well, both create equal value at the job or have the same probability of returning their loan, so then it shouldn't matter.
Then it shouldn't affect our prediction. That, also sounds maybe nice. So what this sort of comes down to is it's saying that we're going to do false positive rate matching or false negative rate matching across the various groups that you might belong to. And so the classification that you get as an individual, well, okay, members of your group should get, actually probably shouldn't have said as an individual, it's a little unfair, should only depend on your protected attribute to the extent that it's justified by the target variable. So to the extent that it's actually predictive. So for example, the probability that I give you a high score with my algorithm, conditioned on you being female and repaying the loan, should be similar to the probability that I give you a high score, conditioned on you being male and being someone who will repay. And so, more generally, we're going to say that the probability that you get a particular outcome from my algorithm should be approximately the same, conditioning on your true label and your membership in a protected class. And that should hold for all pairs of protected class, all possible outcomes, sort of true labels, all possible scores. And this is for those of you who like graphical models. For those of you who don't worry about it. This is saying that we have this y is the thing that mediates in some sense. We should have independence of the r and the a, conditioning on that y. When we manifest this at the level of binary outcomes, that's when we get this realization of this notion as being explicitly true positive and true negative rate matching. So the probability that we're going to say R0 is reject you, conditioned on you being a unqualified woman, should be similar to the probability we reject you, conditioned on you being an unqualified man, probability we accept you, given blah, 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 all the various combinations should be similarly mapped across the groups. What do you like about this as a fairness notion?
It fixes the problem of the previous.
Which problem?
Well, the problem that maybe it has some predictive power. Maybe.
Okay, good. So this is acknowledging that maybe there's some predictive power in that protected attribute, and it's saying that it's legitimate to leverage that protected attribute in your prediction to the extent that it's predictive. That's maybe nice, yeah.
One thing about it is very nice. It's fairness and accuracy. Like the accuracy of the mechanism of the algorithm is not dependent on your attribute of which we like. This is sort of like we're not talking about necessarily outcomes, talking about the algorithm itself and how good it is in predicting.
Yeah, this feels like a constraint that says, okay, if you're making errors on this group, then okay, you should make similar levels of errors on this group. It's an accuracy type of constraint, which maybe feels a little cleaner in some sense than restricting ourselves in the previous way. There was another hand, yeah.
I think this one forces us to give a loan to the right woman. Like if a woman is eligible for a loan, then you should give it to her.
No.
In contrast to previous one.
It doesn't get us all the way there. Who said no? Yeah, say what you wanted to say.
I mean, because it can be that we are just not giving room to anybody. Not men, not women, nobody. All of this is...
You're onto something here. Yeah, so fairness is going to be really easy for just about any fairness notion. Just don't give anybody any loans, and you'll satisfy just, not every, but almost every fairness notion. Not quite, but you're going to want to interact fairness with some degree of accuracy in many cases in order to get to someplace interesting. So this doesn't necessarily force you to give loans to the right women, but it at least says to the extent that you're giving loans in the right proportion, here, that you should give loans in the right proportion over here. It's progress, maybe. Yeah. So I have tried to argue that it's simple to state and understand, relatively easy to ensure and audit again. One thing that I like about this as a fairness notion, none of you pointed to, which this is a fairness notion that incentivizes the collection of better if you design your algorithm and you see that it fails on this, because its false positive rate on women is much worse than its false positive rate on men, this says, go back to the drawing board. If you can't make your algorithm better with the data that you have, go get better data so you can predict better on women.
What happened with the COVID vaccine, right? The COVID vaccine famously had so much missing data for female participants because they ruled out all women under the age of 40 that they could get pregnant. They weren't in vaccine research and they had to actually go out and specifically try and get it to improve their algorithms.
So this, yeah, so that, I don't know that story well enough, but it sounds like it aligns in the sense that this can be a red flag that pushes you to action which could be good. Could be good for the world, both for the projected group on which you're doing poorly and generally for accuracy. You want to object?
I'm still hung up to the 2 slides ago.
Okay.
Y is not a function of X in any sense now. Now, Y is a random variable just like A and R are, okay? So that slide was very misleading, I'm sorry to say. You should
It was an unfair slide.
yeah, you should throw it away. It's, I don't know.
I'm happy to take that. These are all random variables. They have various relationships. If you don't want to think of them as functions, I'm happy.
No,
I'm
it's
happy to.
confusing. It's confusing.
I'll take that. Yeah. I think of them as random variables.
But an algorithm captures a business, and you at no point have introduced the difference between the bank who owns the money and the customer who wants the money. Those are 2 very different roles.
Yeah. We have potentially conflicting goals, utility functions, incentives in this space. Absolutely. I'm not solving any of those problems. Again, I think this can be useful as a red flag. What do we not like about this fairness notion?
It may sacrifice accuracy in the sense that, we have A and B, right? And prediction for B is better. Then by doing this, we just lower the prediction.
Yes, I want to say that again because that's a really important point. This is actually a really horrible thing to have to do when you're designing your algorithm. What you do is you deploy your algorithm and the data, you audit it, you see how you're doing in terms of false positive, false negative rates and all the various groups, and you say, oh shoot, there's this group where I'm doing really poorly. I don't have time to go get more data, I don't have a better way to predict on them. I'm just going to have to intentionally make mistakes on all the other people in order to match my false positive, false negative rates to what I'm doing on that group. That's what this says, is go intentionally be wrong, potentially on lots and lots of people. That doesn't seem very fair.
Would you call that overfitting?
I'm not sure that's the word I would use for it, but it's this sort of, I can't make the analogy work right now, but maybe I'm missing something. And why do you want to say overfitting here?
Can I try to help?
Sure, yeah.
If you look for enough A's, you'll find one that is going to be a bit biased. Okay, people that are 174 height and this color. I mean, if you look at enough subsets, one of them there will be biased. Not one of them, many of them there will be biased. Okay, so the question is how many you are looking at. How many additional attributes you are looking at, or what are the additional subsets you are looking at? Given enough of them, there will always be one on which there is bias. I think that's a theorem, essentially.
Yes, and given a third lecture, which I don't have, we could actually get deeply into issues related to that. But maybe we can return to it as we go along. But the question of which groups that you say we want to protect, and how many of them is an interesting one that interacts in interesting ways with these notions. Yeah.
I feel like overfitting happens because you have little data overall, but here you have little data for some attribute or biased data for some attribute.
Okay, yeah, then maybe that's part of the analogy here. Yeah. So basically what I don't like here is this conflict with accuracy, this demand that says, oh, because you don't know how to categorize this group well or classify them well, now you have to intentionally go around making mistakes on everybody else. Yeah.
But does it make sense to say that this is the only thing I'm trying to optimize for? Like it's a con only if I say that the only thing my algorithm is working towards is doing this.
Absolutely, and all of these you might think about approximating them, incorporating them in an objective function along with many other things, but I think we won't get there explicitly. That's part of what some of the literature does. But again, it's a red flag. If you see that I have a much higher false positive rate on this certain subgroup, you should ask yourself why. Do I not have the data for this group? Is this group inherently problematic for some reason? Are there mistakes in the data? What's going on here? Because I'm having trouble predicting for this group. You should understand why. Yes, and then yes.
Isn't it true for all fairness consideration? Your constraints or your accuracy will be less, it will be less accurate?
Let's return to that question in one slide.
So I think the same way you have data mining, and so now you have to register what you are looking at before you get the data. I think there should be bias registration. You have to say, before you have any data, before you think about, tell me what groups you are going to check for bias, you have to register them.
So
Not ex post once you have the data, because otherwise you are always going to have some subgroup on which there is bias. So you have to decide what kind of groups you want to have no bias in some sense of fairness, and you have to register that in advance, before you look at the data, at the algorithm, and whatever.
turns out you don't need to do that. And also it turns out there are many people who would argue that you shouldn't do that. But first of all, mathematically, you don't need to do that. You can get cool results even without that pre-registration mindset. But second of all, there are people who would argue that it's the sort of unexpected, we didn't know that this algorithm was going to mistreat people at the intersection of two groups, that we really ought to discover somehow, even if we didn't anticipate that they should be protected. All right, one more question here, and then let's move to our next notion. Yes?
So if accuracy is our ultimate goal, and we had an algorithm which gave us perfect accuracy, then in some sense, the fairness issue wouldn't come up, because attributes would only matter to the extent that they give you the correct label. So one way of talking about fairness is to say, well, to the extent that the algorithm is not completely accurate, there's an epsilon. We want the epsilon not to depend on the protected, or we want the epsilon to treat all of the protected attributes equally.
Yeah, so this is exactly in some sense what's going on here. So let me sort of...
Because the condition goes on the y, which was the true answer, and you look at how the distribution is, which is the variance for the same y, that should not depend on a. That was on the previous slide. That was the condition on top of that.
Yeah, so in some sense, I want to basically say this back in another way, which is that separation is really a story about trade-offs. In a world in which you don't have perfect predictors, what separation says is you're going to make some mistakes, and you have a choice about where those mistakes lie. Given a class of classifiers that you have available to you, you can plot these ROC curves, which essentially tell you the best possible trade-offs that are achievable for each of the groups that you're thinking about in terms of true positive rate versus false positive rate. So there's some space of achievable trade-offs for each group, and separation is saying something about how you should navigate among those possible trade-offs and how you should balance the trade-off point that you pick for one group versus for another group. And in particular, if we want to do this sort of false positive rate matching, false negative rate matching, what this says is that what's achievable in terms of fairness is not, everything in here and everything in here. It's everything that's in the intersection of these. And so you can sort of color this achievable region here and say, okay, the fair possibilities are to pick classifiers that can, match these false positive rates, false negative rates across these two groups. And then you have now a space to pick from. This is your design space now. Some of these will be sort of randomized classifiers of, combinations of things. And generally what you're going to want to do is you're going to want to pick something on the frontier here that's, optimizing, given a constraint of a particular false positive rate or a particular true positive rate, is optimizing the other one. And then the question is going to be, where on this frontier are you going to sit? And I don't know how to tell you which is the right point, but that's a space of possibilities. Yeah.
So are you guys advocating for this? Or
I'm not advocating for this.
Right,
This is a particular notion of fairness.
Okay.
You want to argue against it? You're very welcome to. There are also things I don't like about this, but this is just an interpretation of this. Yeah.
One more pro thing that somehow you didn't mention is, at least this notion of fairness, that truth satisfies, right? The previous one, the independence, truth would not satisfy.
That is a good one. I should have said that. Yes. So separation is a story about trade-offs when trade-offs are necessary, and when trade-offs are not necessary, because we can simultaneously get perfect, rate of true positives and perfect rate of true negatives. Then great. Separation says go for it. Be perfectly accurate. It's only when we don't have that option that separation says, okay, we care about those failures and which populations they fall on. And we want to do some equalization there. Okay. Explicitly, I want to go on to the next notion, but I want to spend just a little bit more time on this notion. All right, suppose you have two populations. This is their sort of distribution of repaying the loan in the red population on my computer, and in the purplish population on my computer, this is the distribution of probabilities of repaying the loan. So this person has a 60% chance of repaying the loan if you give it to them. This person has a 40% chance if you give it to them. So we have two populations. I'd like you to turn to your neighbor and discuss what does separation tell us to do with these two populations. What are we allowed to do? What would be fair according to the separation metric if we had these two populations and we had to decide who to give loans to?
Like red and purple are the A.
Yeah, these are my A's, these are my B's. The red and the purple are my A's and B's. Turn to your neighbor. What are we allowed to do with separation? Go. You have to create a neighbor. You have to turn to somebody and say, hello, my name is Katrina. Hi. If you don't have a neighbor, you have to stand up, move. You can turn back to somebody behind you. You can turn to somebody in front of you. You say, hello.
What's the question?
The question is, what are we allowed to do under separation? And maybe how can it go wrong? Well, what could be something bad that you could do that would satisfy separation, but you would be unhappy with it as a way
What are the
of giving out the loans?
expectations here?
What it is, what?
Expectation is higher below, right?
We're going to say this is a 90% chance of doing the good thing.
Yeah, I understand. I mean, like, expectations over reds and blues.
Great question. In the underlying population, I haven't told you what percentage of the population is reds or blues.
Okay, I mean, here A has predictive power, right? Because Y would be higher on average for blue. Like just averaging 0, 9s and 0, 1s, and just averaging 0, 6 and 0, 4. That's what I want.
So yes, knowing whether somebody is red or somebody is purple, or in this case it looks more like pink
So
and
let's assume
blue.
the numbers are such that the average is the same.
No, I want you to take these numbers.
I want to make it more interesting.
Okay, start with this. Alright, turn to your neighbor and try to figure out how you can build a rule that would work with this. You're allowed to say everybody above a particular value gets the loan. Maybe you have a different cutoff threshold in each of the two populations. What are you going to do? Who are you going to give loans to? Turn to your neighbor. If you don't have a neighbor, make yourself a neighbor. Say hello. There are nice people in the room. You can randomize if you want to.
These chairs are too comfortable.
How many loans can I give?
How many what?
How many loans can I give?
Up to you. I'll let you give up the loans. Whatever loans you want to, but you might have in the back of your mind some accuracy kind of goal here. The money on the side, yes.
Which I
Yeah. Okay, for you, I'll say that it is 50% is worth the other one. But I've got a big side payment.
when you're going to let people, when people will buy and you will believe it. So the result of the discussion about what happens when you really have is the time of the year and the spirit of the population.
All right, should we bring it back? And people have some ideas. You know who you're going to give loans to? All right, who's willing to say something about what you decided to do with these loans? Yeah.
So the choice I'd like to make is, well, the only thing I know is whether someone is red or blue. So I'd like to give them the loan with a probability according to what the average is. So maybe I give a blue person on average with 0.5
And you roll the dice?
and yeah, I'd roll the dice. I'd say, okay, the person in blue, I'll roll the dice with probability almost 0.5, and if it's red, I'll roll the dice with probability like 0.3. And then that way I'll pick whether I'll pick them or not. The problem here is that if you're one of the 0.9 people, you're going to say this is unfair because given my probability, the probability of picking me is way too low. So maybe so this would not satisfy separation. But if I want to fix this, I'll either need to lower the probability of picking a blue person way lower to match the red people, or increase the probability of picking a red person. Either way, I'm losing severely on accuracy.
Yeah. So you felt your hands were somehow tied by the separation constraint in a way that was really hurting you on accuracy. Yeah. Other comments, thoughts on what you guys did?
You wouldn't throw a coin with weighted probability. You would just, you have to choose that threshold and it will be a step function to see that. It won't be like a probabilistic that has like higher accuracy. It's just a question of the threshold.
Yeah. So okay. So there's sort of two versions of this question, and I didn't really specify which version it is, and I sense that that people solve two different problems. They're both legitimate problems. So one of them is you don't know those numbers, and you just see whether somebody's a member of the group. And so that's one version of the question, and then you just have to make prediction based on their color. Another version of the question is, suppose we did give you access to these probabilities, encoded in their X's in some way. And I think that's maybe the version of the problem that you're solving, and you're saying, okay, there I'm going to set some threshold. I'm going to set some threshold for the red people, and I'm going to set some threshold for the purple people.
Actually, yes, but also like, whenever you have like probabilities, like throw in the coin, like why?
Maybe for fairness,
No,
accuracy won't help you, but maybe for
I'm thinking
fairness.
if all I know, I receive a person, I know they're red or they're blue, and I know that's all the information I have.
Yeah, I didn't make it clear which model we're in, so that was a totally legitimate version of the problem to
You decide how
solve.
many you
Yeah.
are willing to take, which ones you choose at random.
Exactly.
So the randomness comes on which one. But what you have to decide, how many red, how many blue. That's it. The
So-
numbers.
So yeah, so they were solving a different version of the problem. They only knew whether people were red or they were blue, and in that sense that they had to pick whether or not to give the loan on the basis of the color. A richer version of the problem in some sense says that we have access to information that gives us some probabilities, and then you want to create some sort of thresholding mechanism. So people were thinking about this as the thresholded version of the question. What did you do? Who did you give the loans to?
Do we have a budget of how much loans we can give?
Sergio wanted to know this too. I said, okay, maybe say that once people are
There's a cutoff point where it's worthwhile.
maybe it's worthwhile at 50% because you're getting so much money from those who are
Okay, sure, but then
paying
you would
fees on the
give,
side.
like accuracy-wise, you would give to the blue people, right? But if you want fairness, you would randomize it.
Yeah, so we say that we sort of have our hands tied in some sense. We could classify people as risky or not risky. You could have different classification thresholds for the two populations, maybe. So maybe here you would say, okay, 50%, we're really fine with that. That's a very clear boundary. Here we could take a boundary of 50%. Here, if we took a boundary of 50%, we'd be super accurate, right? We'd almost always be right on people by using that as a threshold. Here, if we took a boundary of 0.5, we'd be wrong a lot of the time. And what separation would say is, that's not okay. So then what are we supposed to do? How are we supposed to pick a boundary?
If you pair them,
Pardon?
if you create pairs.
Okay, so let me increase the threshold. What should I increase it to?
A different threshold.
So maybe
Your
you
choice.
decrease.
So I can.
0.7.
So I can pick 0.7. What's going to happen here? I'm going to be slightly less accurate, but still really accurate. These guys, I'm going to reject all of them.
Oh, I meant 0.55.
Okay, sorry. Okay, 0.55. Okay. I'm still going to be really accurate here and not not so accurate here.
No, it should be 0.4. I do not.
Okay, so I can pick a threshold of 0.4, so I'm going to accept these guys and not these guys. But I'm still going to be wrong a lot of the time.
Wait, what?
No, you
No,
are.
no, 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 no.
Like,
I'm accepting all of them.
Oh, you accepted all of these. Okay, but I'm going to be wrong a lot of the time. And here I'm going to be right most of the time.
But this is inevitable.
Yeah, so we're ending up in a situation where we realize separation is saying sometimes when you have very different population distributions, you're going to have to intentionally make mistakes. You're not going to be able to go around giving some nice clean threshold that makes sense. You're actually going to have to do something that feels irrational in order to achieve this notion of separation. You wanted to say something here?
The practical problem is you have two very different distributions of underlying population. Insurance companies fix this by subsidizing car insurance when they've got too many home loans, right? So there's some really nice financial ways to actually deal with this problem. If you don't have to pick a threshold that makes people feel comfortable. And any firm that says that doesn't really know how to do portfolio optimization. You can actually fix the distributional problems that are the heart of your problem here.
Yeah, so but given this sort of toy problem, we end up in a kind of uncomfortable situation. Yeah, you wanted to say something about it?
Yeah, I think that here it's, for me, the problem is not with separation,
Mhm.
actually with the problem setup initially.
Yeah.
Because like the label is actually, like if it's as much as could be predicted by X, well it's actually not 0, 1 as a distribution, right? For each X, which are here 0, 1, 0, 9 and so on, right? But this would mean that A has predictive power with respect to this, even with respect to this probabilistic Y, even if the expectations were the same, top and bottom.
Mm-hmm.
So we should match maybe not the label 0, 1, but the probabilities to be.
Yeah, so let me repeat back part of what you just said, which is that, even if the expected rate of paying back the loan is the same or very similar across the two populations, we can still get ourselves into trouble with separation because maybe, despite the expectations being very similar, the distributions still look very different, and one of them is much easier to set a threshold for. And so we could end up in a situation where separation is going to force us, if we really insist on it, to do something kind of uncomfortable. Yes?
So I think we come full circle in the sense that we want to not have bias, and in order to achieve the non-biasness between the groups, we need to look at them differently. So we add bias at a different point. So if we look at females differently than males, then the algorithm is biased. I mean,
in some sense, we're struggling with, how to define this thing. We have one more notion that I want to spend time with, but I think we don't have time to do it now before the break. So instead of moving to that, I'm going to save that for after the break. Are there any more questions or comments before we break? Before we break for lunch? Okay, so hopefully where you've gotten to, as I promised, is kind of an uncomfortable place, where I've given you a couple of notions, you don't like either of them, you don't feel like they capture what you want from fairness, but yet each of them, I think, is an interesting red flag. And so that's where we're at right now. After we have lunch, what are we going to do? I'm going to give you another notion that you're not going to like for other reasons, but which is also an interesting red flag. And then we're going to start to interact these various notions with each other to see what happens. And then, time permitting, we can sort of step back and talk a little bit more about this field of algebra.